up. This is very cool because it's a combination, the nexus, if you will, of racing and engineering and competition, etc. Joining us, we've got John Norton. John is a turbo guy, back to the Grand National, but is working on some very heavy stuff over his career. I can't wait to dig in with John a little bit because, it's about smart people, and the more smart people you hang out with, the smarter you get. John, that sounds like you looking at the Grand National in the background. That thing is pretty spectacular. But what I'm interested in is, like, you've done turbo evolution. You've worked with camless engines that fire due to electromagnets. Now you're back on turbochargers. We got a lot to learn from you. I'm excited.
Wow, that's quite a billing. I hope I can live up and share some of the smarts and experience that I've been fortunate to go through over the years. But thanks for having me.
No, we're super excited, and I love the Grand National in the background there. It's kind of interesting to see how ahead of its time. Was it or was it not? Here in the United States, many of our viewers are. Turbochargers have been really adopted and achieved maybe saturation, now. I don't know. That Grand National in 1986, T-Type 85, that was kind of early. There were other cars that had turbos prior to that, but that seemed to get it right and get everybody's attention.
Yeah, and a big part of that was the evolution of EFI. The Grand National had computer-controlled coils before the Corvette did, and it was kind of a leader in EFI technology, and that was a big part of it too. This particular Grand National is my late father-in-law's. He did a lot of development on aftermarket products, but it's real special to us.
Well, it is a beautiful car, and it's a muscular. You can tell by the look. It's as muscular as they get.
Yeah.
Awesome. I believe Stefan is also on. I do not see Stefan Papadakis, obviously owner of Papadakis Racing, and Jeff Racer is also on, founder of Full-Race Motorsports. And so as soon as we see them, we can bring them on as well. All right, I see Jeff and I see Stefan. And so this is the combination of all things performance in terms of BorgWarner, turbochargers, and full race. So let's go with Jeff, who is the founder and CEO of Full-Race Motorsports. You guys partner with folks like John to build the best product so that Stefan and his team can go out and win races in rally and the world like that. So let's talk about Jeff and how you got started. I understand that you Jersey kid, got a great education, and turned your dreams into reality.
Well, first of all, thanks a lot for having us, Joe. It means a lot to be on ePart Trade, and we're really excited to be here. And I've been into turbos since I was a little kid. My father had a Toyota Supra Turbo when I was like 12, 13 years old. So I went to engineering school because I love turbos. And when I graduated engineering school, there was only one thing I was going to do, which was work with turbos. And so one thing led to another, and here we are today. But yeah, I'm really fortunate to work with people like John on the engineering supply side. And then I work with race teams like Stefan and his guys on the race side. So I'm really happy to say that we have some fantastic partners.
Did you spend any time out at Englishtown, New Jersey? It's
a few weekends there.
It's sad that we don't have it anymore, but its legacy lives on in people like you who found their passion and took it on to new places. And let's get Stefan into the mix. Obviously, got the race car in the background. Turbos, turbochargers equal power. You can't have a second of lag, and that's why these guys are involved. It seems like it's working for you.
Yeah, we worked with BorgWarner for 8 or 9 years now, since the EFR line came out, and it's been a great relationship. We really love the product, and they're continually improving. And since we're always building new cars and continuing to improve on our end, there's a lot of synergies there.
You win the background of the day so far for my vote. EFR standing for Engineered for Racing. And let's delve a little bit, starting out with you, Stefan, since you're on and in front of us. Like, what do you need? What do you look for? What are the challenges that you present to the engineering side to be solved? You want to set these guys at work. What is it that you came to them or want them to attack that makes you and your guys faster?
So number one for us, it's going to be reliability. with racing, you really have that one opportunity to go out there and make sure, you know, you go out there and try to win. So reliability has always been paramount, and the BorgWarner guys have been, the product has been excellent as far as reliability. Beyond that, it's making the horsepower that we need, and also great response, transient response. Because with the drifting, the driver's doing a lot of improvising, chasing the cars and going around, you know, the course. We do want maximum power, but transition response with the turbocharger is really important as well. And we really get that whole package with the EFR components.
And so that means eliminating, you know, there's a couple of things that the layperson knows about a turbo, and turbo lag is one of the things that it's something that exists. But in racing and what you're doing, I would imagine that is the ultimate enemy, trying to build wheel speed to drift. And if you run into a lag situation, it can all go downhill. So eliminating or reducing lag, how have they been able to help you?
So one of the ways is with the EFR turbochargers use a very lightweight turbine wheel, the titanium aluminide. I think I'm saying that right. And having that low inertia wheel really helps, and the sizing the turbo right. So we work with not only the BorgWarner engineers, but Jeff over at Full Race we discuss the engine that we have. So we run a 3.2 liter inline six, and the RPM range, which we really want, we have a broad range of RPM from 3,500 all the way up to close to 9,000 RPM. And we want as broad of a power band as possible. And with drifting, you know, you're on the throttle sometimes at 4,000, sometimes, you know, all the way up to 8. And we're not trying to necessarily accelerate the car at peak accelerations. We just need a lot of power as broad as we can. And we tend to size the turbos a little bit smaller than you may put on maybe like a quarter mile or a half mile or 1 mile car. And we're less worried about efficiency and more worried about, you know, just getting that spool up and quick as quick as possible. And technically that works by having the smaller turbocharger that will make the power that we need. So we'll have a turbocharger that flows, you know, 900 horsepower in maximum flow and pretty much extract the full 900 horsepower of potential. We'll be a little bit down on efficiency, and our air intake temps might be a little bit higher than they could be with a more efficient one, but we tend to have a little bit more of a responsive turbo on that end, and we'll tend to spin the turbos relatively fast near their maximum designed RPM, and we keep tabs on that with the turbo speed sensors, and we can data log the turbo speed into our electronic control system, our ECU, and we can make sure that we're always within the, you know, the design parameters of the turbochargers we use.
Interesting. So Jeff, jump in here, and we just heard that the race team and the people who are putting the power to the ground. You as the engineer, you have to take all those needs and wants and put them into a part that is going to work and be reliable. We already know that you know, specialty metals and come into play here to make things live in that environment. So why don't you tell us a little bit more about these turbochargers?
Sure, Joe. I have a quick presentation I'm going to run through, and hopefully help some people understand this a little more. Can you see the slideshow screen?
I can, yes.
Okay, cool. So obviously this session is BorgWarner, Full Race and Papadakis Racing. So I'm just going to run through a few things that I felt would be interesting to the viewers. And so right off the bat, I'm going to tell you that right now we see 3 important mistakes that a lot of shops are making all the time. And we're going to talk about what they are and how to avoid or to correct them. So obviously I'm Jeff, and most people may or may not have heard of Full Race, but I started Full Race 18 years ago. And in that time, I've seen almost every possible mistake applied to turbocharging, and I've made a lot of those mistakes myself. So I'm going to try and help everybody understand what they are and how to correct them. So really, there's only 3 things that we talk about at Full Race. We joke about this, but it's turbocharging, turbocharging, and turbocharging. And over the years, we formed an amazing set of partners. You can see the logos on the screen. These are serious players, and you know, we have long-term relationships with these companies. So it means a lot to us, but it also helps us step our game up. Positive reviews from customers, this is really what keeps us going. And we're lucky enough to get these things every single day. So I know our customers are attending these webinars. Probably some of them are tuned in right now. So I just want to stop and say thank you. And we genuinely are super dedicated to making happy customers. We have customers in 90 countries. And in that 18-year time that we've been in business, we've seen the thinking about turbochargers change. And picking a turbo used to be a lot less exacting than it is today. I think people would just talk to someone and figure out what works and grab any random turbo and try it. But that's just not true anymore. And when I say that, I'll typically hear from somebody who says something like, nope, none of that's true, or new, but been using turbos forever. Nothing's changed about selecting a turbo and making horsepower. And those folks are probably getting the turbos from any of the big warehouse distributors. And those companies are great, but we're different. We are specialists. Full-Race creates unique and custom combinations, and we supply hard to find turbo hardware, manifolds, and kits. So every day, we help professionals make decisions about their turbochargers. And most importantly, we crunch the numbers for our customers for free. In other words, we match. And even though we're a small company, we help someone somewhere with these calculations every single day. And our customers are racers. They're at the elite level, and they want to blast down the track as fast as physics will allow them to. And they want to push their hardware to the limit, but not destroy it. And so really that's why we do the math. And the fact is, not doing the math can cause a lot of tears. We help our customers to avoid this. Turbos are being pushed harder than ever, but nobody can beat physics. And with modern turbos spinning anywhere from 80,000 RPM to 200,000 RPM, the hard limit of 560 meters per second tip speed is the universally accepted maximum speed where a turbocharger will begin to fail after 560 meters per second tip speed. And so in that case, you would get what's called a wheel burst. And in the case of a turbine wheel hub burst, the turbine wheel gets torn apart by centrifugal force. And so basically the heaviest spinning portion of the turbo, which is at 1700 degrees Fahrenheit, it explodes into shrapnel. And everybody hates it when their expensive performance parts fail. Obviously losing races sucks, but hurting yourself or hurting other people, that's a lot worse. And as Steph was talking about, using a turbo sensor to monitor turbo speed, this is something that's actually relatively new in our world, and it's really proven itself value. So we'll get into that more in a minute. So this is an example of a customer I worked with in Dubai with a Tarmac Rally Subaru. It was a 2.5 liter engine that was revving to 8,000 RPM, and I had 36 pounds of boost. His tuner picked a turbo. It was supposed to reach 900 horsepower, or I say it was advertised as reaching 900 horsepower. And so when his first turbo failed at 700 horsepower, he thought it was a fluke. But then both turbos failed due to overspeed. After he replaced the bad turbo with the backup, that one shortly failed. And what you can see here is there's a red oval highlighting points 5 and 6. And so 0.5 is 7,000 RPM, 0.6 is 8,000 RPM. And as you can see, we are completely off the map. And this is the definition of overspeed. He's exceeded 560 meters per second by a large margin and absolutely should anticipate a turbine wheel hub burst. Now, if this guy had asked us to do the calculations originally, he could have picked a higher flowing compressor and safely operated on the mat. So Full-Race performed our analysis and we came up with a better match. And we'll talk about aero a little bit later, but really what we did here is increasing the inducer of the turbo, of the compressor inducer from 62.6 millimeters to 67.5 millimeters, and no change to the exducer. It allowed for proper safe operation on the map. And you can see the red oval points are completely on the map. This shows off the map, a smaller turbo, slightly bigger turbo, completely on the map. The end result was approximately 25% gain in airflow and a negligible increase in inertia. And so this was a big win for this customer. But, you know, we talk about overspeed, a turbine wheel hub burst, shrapnel. I really want to illustrate the amount of energy in a turbine wheel burst. And so we'll compare a racing turbo's velocity to other high velocity items. At sea level, an object goes supersonic above 767 miles per hour. A bullet from a 357 Magnum is about 917 miles per hour. And a modern performance turbo is 1,342 mile per hour tip speed. So that's Mach 1.7. And this really is dangerous if this comes apart. The fact of the matter is, if the turbo's rated speed is exceeded, it's not a question of if the turbo will fail, but when. And running a turbo into overspeed creates an unsafe environment for anyone who's driving, tuning, or even near the vehicle. So if you're on a dyno or around a dyno, it's a very good idea to use a turbo speed sensor. And I highly recommend that you don't ever stand near a dyno or a vehicle when making pulls, whether it's a turbo that could come apart or anything. You know, it's just people tend to underestimate the amount of energy that is in a high horsepower engine. The next mistake a lot of people make is they think a higher power level needs a larger wastegate. And there's a lot of configurations for wastegates. There's internal wastegates, external wastegates, recirculating, dumping to atmosphere. There's many ways to do it, but it's a myth that a bigger wastegate is better. Wastegating is exactly what it sounds like. It's actually wasting energy. And this keeps the turbo from spinning too fast and creating too much boost. It is possible that you can get so much exhaust volume that a fully open wastegate won't prevent runaway boost, and that's known as boost creep. But on the other hand, if the wastegate is oversized, the turbo speed will drop too fast when the gate cracks open, and boost can be very difficult to do. So it's just as important to match a wastegate solution as it is to match the turbo. You'd be surprised how little wastegating occurs on a high horsepower engine. And this is actually going back to that Subaru, Tarmac Rally Subaru in Dubai that we did. This shows at 700 horsepower, it needs approximately a 26 millimeter wastegate port. So it's a lot less than most people think. The final mistake a lot of people are making, and I used to think this too, is that you need a lot of high oil pressure with a ball bearing turbo. And everyone's heard the saying that oil is the lifeblood of your engine, but obviously that's been drilled into us since we were young and learning how to turn a wrench. And we've also heard that more oil is better. But when we went into the lab to test the ball bearing turbos, we were surprised. It was interesting to us, but the high oil pressure actually acts as a brake and it slows down the turbo. We believe that increased turbo performance from a safe reduction in oil pressure is a real possibility for racing applications. One of the main ball bearing advantages is that continuous high oil pressure is not necessary. You only need a thin oil film between the rolling elements and the inner and outer races of the bearing. And turbocharger ball bearings are very hard. Modern ball bearings are typically made out of ceramic materials. And as a result, they're tolerant of dirty oil and they tend to chew through contaminants that would otherwise damage a journal bearing turbo. So I'm always a little scared to tell most people about reducing oil pressure because you can go too far. Not having enough oil obviously damages engine parts. But if you're careful, it can be done properly. And some of our clients deliberately run ball bearing turbos with low oil pressures and have fantastic results. So one more quick note on this point before I move on is that a BorgWarner ceramic ball bearing turbo can actually handle at least 10 times more thrust load than a traditional journal bearing turbo. And I say at least 10 times because the thrust rig at BorgWarner is only capable of generating 10 times more thrust. And we haven't been able to damage a ball bearing turbo due to thrust in the lab. So that's a big statement. That was kind of a surprise. But when we were doing that, one extra surprise we saw in the lab was that for most turbos, water cooling does almost nothing while the engine is running. And a lot of people think you have to water cool a turbo, you got to keep the turbo cool. Well, the fact is water cooling is doing nothing while the engine's on. As long as the engine's on and the water pump is spinning, the difference in coolant temp in versus coolant temp out is only 1 or 2 degrees Fahrenheit. And so this image here shows water lines properly plumbed. Your inlet is coming in the bottom and it's leaving at the opposite side's top. And so BorgWarner's guidelines state that water cooling is recommended for iron turbos, but it's mandatory for aluminum bearing housing turbos. Water cooling's main benefit actually occurs after the engine has been shut down, because the heat in the turbine housing and exhaust manifold will soak back into the turbo center section. And if the water isn't plumbed correctly, this intense heat from the hot shutdown can destroy the bearing system and the oil sealing piston rings behind the turbine wheel, and that's circled in red. And the reason for all this is a phenomenon called thermal siphoning. And this pulls water through the turbo center housing even after the engine is shut off and the water pump has stopped spinning. So obviously we know heat rises. Therefore, if the water is running through the turbocharger and can escape unrestricted after absorbing heat, it will rise through the cooling system and pull cooler water into the turbo along with it. The corollary to this is vehicles like John's Grand National in the background, and air-cooled Porsche. These are vehicles with relatively low exhaust gas temperatures and no real water cooling circuit. And so obviously there's no way to water cool that turbo, and water cooling is not an option. Therefore, the solution is to use a steel bearing housing with a 90-second turbo timer. And as long as you have a turbo timer to keep the car idling down after a heavy use period, it'll keep the heat out of the bearing housing. So you need to match the oil and coolant solution, you need to match the wastegate, and you need to match the turbo. So I'm quickly going to run through two examples of what matching accomplishes on the track. You can see this Supra in the back of Papadakis's background, but Toyota and Papadakis Racing are the most winning drift team in history. And so we've been working with them for years. We've won championship with them, and we were really excited when they came to us with this brand new Supra. They asked us to spec a turbo and a wastegate and manifold solution that could win a Formula Drift championship. We started by performing the same analysis we do for all of our customers, and we came up with two matches. The first match was an EFR 8474 for smaller tracks, and then the other turbo was an EFR 9280 for high horsepower tracks like Irwindale. The team scanned the engine and engine bay for us, and we got started engineering the turbo kit. This is the front view, the side view, and this is the bare manifold design. Then the manifold was printed, 3D printed in plastic for a physical test fit. And when all was said and done, the end result at 38 PSI boost was 1,098 horsepower and 950 foot-pounds of torque. This was 3 times the original engine output. For an all-new car with an all-new engine, we had high hopes, and we weren't really sure how it was going to work out, but everything was going smoothly. So during the first time in Formula Drift competition, driver Frederick Osbo put the Supra on top of the podium. First place in its competition debut was obviously what this thing was all about. And Ed Laux from Toyota Marketing really summed it up. He said, "I can't believe how seriously they worked the motor. They designed and engineered what is proving to be a very competitive, super powerful, and great sounding Formula Drift racer. As with their previous Toyota race cars, this team knows what it takes to succeed, and the hard work is paying off at the track." And we'll get into this a little later, but we also just won at Irwindale last weekend, so super excited. Next up is Honda Performance Development's K20 engine for Robin Schute's Pikes Peak Racer. This was a Wolf GB08 chassis. They asked us to calculate what was needed and determine the right turbo, wastegate, and manifold to win a 12.5-mile race at elevation. We ran the numbers, and the best choice was the EFR 8474. We had a target of 35 PSI boost to achieve 685 horsepower at sea level, and that's what's plotted here. This is a nice, comfy match with plenty of room on the map, super conservative, and pretty typical for a sea level match. But things change a lot at 14,000 feet elevation. And so this is the turbo match at the top of the course. Same engine, same everything, just showing the difference between sea level and 14,000 feet. Previously on this one, we were at 35 PSI boost and we had room on the map. Now we're out of map and we're only at 25 pounds of boost. So this really shows what elevation does. So we could only sustain 25 PSI boost before entering overspeed and going off the map. And this is a high stakes race. We really wanted to win Pikes Peak, and turbo failure just was not an option. So 685 horsepower at the bottom of the peak, and at 35 pounds of boost. And at the top of the peak, we went to 580 horsepower at 25 PSI. And you can see the final point is almost off the map, but not quite. And I really wanted to illustrate this difference in altitude, turbocharger performance, because it's hard to appreciate unless you do the math and actually plot the points. On race day, Schute's run of 9 minutes, 12.5 seconds was the fastest full run up the course, and he beat second place by 11 seconds. After the race, Robin said, "It all came together with the engine and the turbo to really get the most out of the car. All the modifications meant us ending up with a weight of just 568 kilograms, which at 685 horsepower gives us a similar power to weight ratio to that of an early 90s Formula One car." Some companies try to serve everybody, and Full-Race, we serve the obsessed. We aren't just fans. And the fact is, when you need a properly matched turbo, we are the people to talk to. And this is how you talk to us. Anybody listening, please open another browser tab to fullrace.com/wholesale and fill out our wholesaler application. We'll set up an account, get you on the schedule. And so I want to bring it back to the guys on the call today with me, John BorgWarner and Stefan of Papadakis Racing. All right, Joe, take it there.
Thank you very much. Well, my knowledge just went from little to a lot, and I think it is great. And anybody out there who has a question, feel free to put into the comments section. But let's dive in with John. John, from the BorgWarner perspective and engineered for race, I love the idea that we are dealing with like off the shelf stuff. Like this is the part that works well with the match that we have designed. That means that you guys have got a wide variety where they're able to select something that they know is going to work and it's going to be reliable. That takes an element out of it. Speak on that a little bit, John.
Yeah. Our product line, EFR, it is a wide range. It goes from a 62 millimeter compressor all the way up to 92 millimeters. So it's a horsepower range between around 450 horsepower up to 1200. And there are several different rotor groups in between. But the reliability is really impressive. If you think about all the testing that we do to make that happen, we have to validate towards commercial vehicle standards, which means the turbo on a commercial vehicle, like an over-the-road truck, is good for 1 million miles. So those same kinds of tests that are applied to commercial vehicle are applied to EFR and our other performance race series, which is Airworks. And the durability has been fantastic. If you think about all the different race series that we're involved with and the successes that we've had, we've 24 hours to Daytona, 24-hour Le Mans, 12 hours to Sebring, Petite Le Mans, all of those have had EFR wins at one point or another. And to think about Formula Drift as well, you've got the on and off throttle and all the transient responses. You need a wheel that can survive those stress levels. So the engineers and the team at BorgWarner, they put pen to paper and put their best practices in place to create a product that's very durable. Just thinking about one little aspect being compressor wheel fatigue life. If that is not in check, then the wheel isn't going to be able to go through as many cycles as it does, and you'll have a wheel failure and then, of course, lose the race. But so that's one aspect. Another that comes to mind is 12 hours of Sebring. Some people refer to that. If you can survive it there, you can survive 24 hours at Le Mans, no problem. And the reason is the vibrations that are experienced at Sebring are extreme. They intentionally don't improve the track surface to make it a challenge. And the cars literally bounce off the track surface and they porpoise as they go along, and you're just really getting pounded. And thankfully, we've been able to hang in there, and we're proud to say that we've been able to support many motorsports teams that have been successful.
Excellent. And I see some questions for Jeff in the comments section. I'll throw a couple out and we'll talk to a couple of the parts and pieces that people are interested in. Feel free to put into the comment section one way or another. Follow these guys on social media and definitely check out epartrade.com because there's going to be a whole bunch of information there after the fact. This one from Derek. What is your opinion on heat treating the turbo housing? There are a lot of turbo repair companies out there. Any suggestions on how to choose one? This is a multifaceted question. And how does a company go about having their turbo spec'd by Full-Race? That's for Jeff.
Cool. So I think when he said heat treating the turbine housing, I assume that he probably means ceramic coating. And I think coatings are a great idea on turbine housings for really two reasons. Number one is it stops corrosion. And corrosion is a big issue on older turbos, especially when the turbine housings are made out of iron. But a lot of the newer turbos are made out of stainless steel. And so the ceramic coating, corrosion isn't so much a benefit, whereas just reducing the heat emitted from the turbo is a huge benefit. So on top of the coatings, we also really like to use a turbine blanket, just additional insulation and anything you can use to reduce ambient temperatures in the engine bay is really a big benefit.
Very interesting.
Second point, you asked a lot of turbo repair companies out there. There's a ton of them. Any suggestions on how to choose one? That's a tough one. There's a lot of things that happen when a turbo fails. And oftentimes you may find that a replacement center section, just replacement core, as some people call it, is a equally cost effective and higher reliability, durability solution than remanning. So I don't really have a solution on how to find somebody who can reman, but I would more often than not suggest looking at a replacement center section than necessarily repairing one. And then to the last question, which was how does a company go about having a turbo spec by Full-Race? Just email us wholesale@full-race.com. And we'll set up an account with you. We'll go over whatever your questions are. We can spec turbos, do some matches. Just anybody from this is obviously a wholesaler, business to business type client. So just shoot us an email there and we'll get you all set up.
Excellent. Excellent. Yes, you guys want new business. That is the whole point of this exercise. I think it is great for people that are logging on. All right, Michael has got a next question regarding, for the panel, engine oil quality and viscosity to prolong turbo life and smooth turbo operation. What are your recommendations? What do you think on that subject? Engine oil quality. What do you guys like to use? What works? What's best?
John, you want to take that one?
Yeah, I'll start it off. The engine quality is important. It's obviously important because of the speeds and the clearances that we're working on. We're in the micron level of clearances. But I'll go ahead and say that it's even more so important when you run a journal bearing turbo, because the journal bearings are bronze based and it's a very soft material. And if there is particulates, Jeff had mentioned the proper shutdown techniques so that and water cooling so you don't avoid coking, and the coking would create some hard particles in the oil. You definitely don't want that. If you do have particulates and coking in the oil, if it goes through a journal bearing turbo, it runs the risk of getting lodged into the soft journal bearing parent material, and of course that will cause scoring and scratching. For the ceramic dual row ball bearing and EFR, it's less susceptible to it because the hardened ceramic balls and also the hardened races, they tend to chew through any kind of particulate matter. You can take it to an extreme and definitely fail it, but it's less susceptible than a journal bearing. And if you think about the function of the oil in the bearing cartridge, whether it's the journal bearing or ball bearing, it serves as a hydrodynamic cushion, and it serves to dampen the vibrations. So as the rotor group is spinning, and you'll have forces that want to move it, maybe it's G forces from the engine or the vehicle, or the rotational forces, it's going to want to push it towards the limits. and the film of oil will hydrodynamically dampen or cushion those kinds of movements. So the presence of oil is definitely important. The quality of oil is also important. If you go too long, then you start losing those hydrodynamic properties. And then, of course, cleanliness is important as well.
Very, very interesting. Next question, just in terms of the billet wheels that everyone's using, the billet compressor wheel. This is something that we've seen a lot. It's showpiece. It's jewelry out on the tables at actual trade shows. You can't walk through a trade show without seeing them everywhere, and they're awesome and they're cool. Obviously, CNC machining and that technology has made it happen and possible. But you know, what is your take on that? Like, we're seeing it everywhere. It seems like it's the next thing is important. Give us some discussion on that, billet compressor wheels.
Okay. Billet wheels are made from a billet or a forging, and they have the advantage of having stronger structural integrity than would otherwise be available through a bar stock or a casting. So the parent material on a billet, if done properly, is stronger. And so what that allows the engineers to do when they're developing the aerodynamics is to take advantage of those material properties and thin out areas that otherwise would have to be fairly thick for stress reasons. And then the thinner you have the blades, for example, on a compressor wheel, the more airflow that you'll have, because you've got less material and more air gap. And if you think about the revolutions per minute, you know, these things spin at, Jeff mentioned 200,000 RPM. That's for some of our smaller ones. So if you have just a little bit less material for each rotation, multiplied by all those air gaps, you're going to flow more air. So a billet wheel affords the opportunity to thin out things and increase the flow. And then also another benefit that may not be obvious is on a cast wheel, you have to have the blade shape such that the blade can be pullable. And what I mean by that is there's a series of fingers that go around the casting, and during the casting process, they have to extract and move outboard to eject the blade from the casting. Well, with a billet wheel, you machine it with a 5-axis mill machine. So it's feasible that you can create blade shapes that you can only do in that process rather than cast, because you don't have to. You're not constrained by the pulling. You know, you don't have to pull the mold away from the wheel. So there's several advantages to billet, and it is quite popular. You'll see anodized billet and kind of blingy, but even a bare raw machined, fully machined wheel looks very nice. It's the bright shiny aluminum, and if you look closely, you can see the tool path for all of the passes that the 5-axis mill machine has created.
Where would we be without that? Who knows? A question coming in regarding is there an EFR turbo for your Grand National back there? It's the question from Richard out there. Wants to know something similar to one of your competitors that might be for the GTX. What about you guys for your Grand National?
Well, Joe, the EFR turbos are, as Stefan was mentioning earlier, the turbine wheel is made of a very lightweight material called gamma tie. And it's an incredible material, but you can only make a turbine wheel so big. And as Richard's asking, he's asking for a monster turbo. We actually cannot use this material for a turbo that's that large. And so there is no EFR turbo that is that size, but BorgWarner does have what's called Airworks turbos. And that's their traditional kind of drag racing, not response-based, not gamma tie. But this brings up an interesting point. And if Richard's looking at a turbo in this size, that's a monster turbo. And so it's either a dedicated drag car using 2 of these, or maybe it's a dedicated drag car using 1 of these. But in a lot of applications, we found that using 2 EFRs can often outperform using 1 larger single turbo. And that doesn't necessarily mean 2 EFRs, but more often than not, twin turbos really does work. And so if you're looking at a turbo like a GTX 55, you might find that 2 slightly smaller turbos could actually deliver larger, greater performance than the big single. And I used to be a big single turbo only guy, but I learned the hard way. Twins really do work.
Wow. What do you guys dream about when you're talking turbos at the shop? I know that there's what we have now, which is amazing and far beyond maybe what you dreamed 10 years ago. But where is your attention for the future, and what do you see happening with this technology as it continues to evolve? Start off with Jeff, and then John, dive in on this.
Sure.
Well, for me, my day-to-day is racing. And I'm an engineer, and I love turbos and engines in race cars. But it also drives me crazy is seeing how cool the stuff is on the OE side. We have, e-turbos and e-boosters and a variety of other electrification technology that are really difficult to get adopted in the aftermarket, and control systems. And there's just a lot that goes into making new turbo tech work in what we know as the racing world. So I'm super excited for the future, but I also realize that it is often a way bigger hurdle to adapt the latest electronic technology to a racing application.
Yeah, and from a BorgWarner perspective, electrification is high on the radar, or big on the radar. As a corporation, BorgWarner has invested a ton of money into the electrification, not only for the turbo front, but for power drive systems. And they've got solutions for an electric motor in all sorts of locations, whether it be on the front end accessory drive, an alternator starter kind of setup, all the way to hub motors, to the wheels, and all the different locations in between. But from a turbo standpoint, electrification can mean several things. Two that come to mind are the e-booster and e-turbo that Jeff had talked about. E-booster is basically an electrically driven compressor stage, so it's almost like a standalone supercharger. And then e-turbo adds a motor generator set to conventional turbos, so you can either spool it up instantaneously to get rid of that lag, and then also, instead of wastegating, you can generate and turn some of that energy back into the battery pack. But unfortunately, those kinds of developments take a lot of money. And what often happens is a partner will come in from an OE standpoint, and will go forward and invest in a program. And that partner, of course, wants to own the rights to it, the control systems, and their own way to control it. And oftentimes, each manufacturer has their own way to control it. And so that leaves the aftermarket kind of out to lunch, if you will, because there's not a generic way to take one of these devices and then apply it to anything. So that's the unfortunate part. But like we've seen happen in racing over and over and over again, technologies sometimes start at the OE level and then work their way to the aftermarket and performance. And this might be one of those cases.
It's exciting, though. It's exciting to think about, to see where you guys have come. We're getting a little short on time, and then we'll hit a break. We'll continue with the show. Everybody, obviously, keep posting. And if you're interested in Jeff and what's going on here, you're going to go to epartrade.com and hit their site and sign up, and you'll get information. But Stefan and Jeff and John, I'm thinking about how far we've advanced with this technology. How far have we advanced in terms of adoption of this? Do you feel like we're still maybe scratching the surface of the potential of this power plant? Stefan's got a car makes 3 times what it made. Those numbers are insane just a couple of years ago. So how far along are we in the evolution? Let me start off with John, and then Jeff, and then Stefan as the team owner and driver.
Yeah, you think, turbos have been around since, I believe, 1962 was the first OE turbo, and you think we'd get it right the first time. But we always develop aerodynamics and continue to improve. The tools that we use, the CFD, computational fluid dynamics, those tools continue to evolve, and so does the experience level of the PhDs that operate it. So we continue to learn all the time and continue to push the envelope, and you see more and more power potential from a smaller and smaller package. So a turbo that would otherwise not fit in an application, you keep developing the aero and increasing the flow and the power capability, and you make it more power dense. so you can create a lot of power from a small package. And I've been in the turbo business since the 90s, and it just always continues to evolve. And I'm not sure where the end is, but to look at the impressive results that Steph has done, over 1,000 horsepower in that new engine is just mind blowing. And if you would have talked about that, I don't know, 10 years ago, you would have thought that'd be never would be possible, but here we are.
Amazing. Jeff?
Yeah, I've seen a lot of trends come and go, and it's been a real pleasure getting to work with guys like John and the BorgWarner team, because I get to see what's happening at the OE level. And we've been influenced by some very smart and forward-thinking people. And so when I started, I was a young teenager going to Englishtown and watching Steph Papadakis drag race a rear-wheel drive Civic and break records, right? And back then, turbos were a lot simpler, and you couldn't buy very many cars that had turbos on them at the time. Now, fast forward 20 years, you cannot go to a dealership without buying a car that has a turbo. It's actually difficult to buy vehicles that don't have turbos on them anymore, right? There's a few, but there's not that many. And I think that says a lot, because 20 years ago when we started doing this thing, it was just a fringe thing for a bunch of guys who are racing and having fun. And now we see that this is actually a strategy used to reduce CO2 into the atmosphere without making really slow cars. And, I've really enjoyed this whole path. I never imagined that this would actually lead us to Ford's doorstep or otherwise. I just wanted to make some cool parts for myself and my friends' race cars. But truthfully, working with Steph has been a real pleasure. And, before I turn it over to you, Steph, I also want you to give me a 20-second overview of what happened at Irwindale, because we haven't even caught up since Irwindale, and I'm dying to hear what happened out there.
Sure. So Irwindale was our last drift event of the season, and it was two rounds. We did a Friday event, which was round 7, and then Sunday was round 8. And we won the round 7. Everything worked great. And then we actually had an engine problem after everything was finished. Frederick, the driver, was doing some donuts, and we had a main bearing for a main bolt failure in the bottom end. And we just reached the limit of the next component of the engine. And we were able to put the spare engine in, and we ran on Sunday again. Ended up 4th in the whole championship. So it was overall a great season. But that's kind of how we work is we have a goal, and this year has been getting the super competitive and getting a certain, over 1,000 horsepower. And then we find if there's a reliability challenge, and then we repair that and make it better. And the next year, keep moving forward. And it's been a really fun year developing the new car, and, looking forward as far as turbocharging technology, when you guys start talking about the e-turbos and having that ability for a little electric motor to spin up the compressor and reduce or actually eliminate the turbo lag is really exciting. So that's something I can't wait for in the future.
Very exciting. It is all very exciting. Stefan, good luck, obviously, in the future. We're going to be watching and love what you're doing with drifting, and just the idea that you're making over 1,000 horsepower. And thanks to John and Jeff and what they're doing. And you guys are Englishtown guys, drag racers starting out. It's just awesome how this community that is motorsports, earlier John Kilroy called it a tribe, how it's all connected one way or another. Everybody kind of on the quest for speed. And to have fun and do it the right way. Thank you, gentlemen. Again, to our viewers out there, you can find these guys on social media, of course, epartrade.com. John, love the Grand National. Jeff, love the knowledge. And we love what's going on. So thank you so much, Stefan. Appreciate all of you guys here today.
Great.
Thanks
you guys
for having us.
Thank you. Bye-bye.
All right.
Registering on ePartrade is easy. Fill out your name, email, phone number, and create a secure password. Next, select your business type. Choose supplier if you're looking to display products or services and connect with buyers. Choose racing business if you're looking to find new parts and connect with suppliers. Choose race team if you own or are a member of a professional racing team. Begin typing your company name. We most likely already have your company in our database, which you can select from the drop-down. Then, enter your job title. Choose Claim Company if you'll be editing your company profile. Other members of your company can choose Join Company if they'd like to use eParTrade as well. You can view and agree to our terms of use here. If you'd like to receive our weekly newsletter, choose Accept. Click Register Now, and your registration will be submitted for approval. You'll need to confirm your email once it goes through. To keep our platform industry only, you'll be approved shortly after. If we require additional proof of business, we'll reach out. Welcome to eParTrade.